So we introduced combinational circuits last time and the time before that, and you also saw how to write some simple combinational circuits, how to express them in Bluespec. Today we are going to tackle slightly more complex combinational circuits and see what are the new issues that come up. So just a reminder, even though you know this, but I want to repeat this because this is very important and people sometimes get confused about this. So Bluespec is a language for hardware design, or if you want, it's a language in which you express pictures, in which you express circuits, which traditionally have always been drawn using gates and wires and so on. Interconnected boxes, and the boxes can have whatever meaning. Now, boxes in our case happen to be Boolean gates. I mean, they can be very complex gates, but essentially you start out with ands and ors and keep building bigger and bigger things, and they have inputs and outputs, and by naming things we connect them. You know, that's what the high-level language does. But this is where the difference comes in from another program that you may use for drawing pictures, say PowerPoint or something. In our case, the boxes have very definite meaning. If you give it some input, it tells us what the output is. So once we have composed this circuit, we can still ask the same question, that if I supplied the following inputs, what is the output I expect from this circuit? So, you know, this is very important. So what that means is that on one hand we are drawing pictures, but on the other hand, you know, we can simulate it too. We can give it some input and some output will come out of it. So you should never forget that the primary goal of a Bluespec program is to help you design efficient circuits. The fact that we can also simulate and see, given this input, it produces that output, is a bonus. It's a benefit. When I was an undergraduate, there was no such tool. You know, we used to actually design pictures, right, and work it out by hand. You know, if I put it 0, 1, 1 here, what will be the output coming out of it? But the level of circuits you're designing and you're going to be designing in this class are so big that simulation is an essential part of it. So we always talk of functionality, and whenever we talk of functionality, we don't mean exactly what circuit is being generated. What we mean is the input-output behavior of the circuit. So another way to look at this is, look at this 2-bit adder, right? Whatever. Right, adder, and again, you know, it has, you can look at it in two different ways. So you look at it, you say it's a program, looks like program in somewhat different syntax, but any other language. But really, the reason we are designing this program is because we want to generate this circuit from it, and then given the circuit for full adder, we can go further down and see, this is this is the circuit we are describing in terms of ands and ors, you know, given this description. The side benefit of it is, I can also simulate. So I say, oh, if you apply this add to circuit to values 1, 1 and 0, 1, then the answer is going to be 1, 0, 0. So this is the simulation behavior of the circuit. You can simulate as much as you want. You can keep feeding it different inputs and see what output you get out of it. So again, the caution, in spite of the fact that Bluespec programs, like programs in any software language, do produce, given some input, some output, that's a benefit, that's an added bonus. The real reason for writing Bluespec program is because it's generating a circuit. Because if it was just input-output behavior, we could have done it in Python, C, language of your software language of your choice. This is a hardware language, and we are extremely interested in understanding what hardware will be generated. So you have to make sure at every stage of the game, you know what hardware is going to be represented by this thing. So with that idea in mind, let's look at today's lecture. All right. So if you see how Bluespec actually compiles into circuits. So what is Bluespec compiler is essentially, given the Bluespec description, generates a gate description, which is often referred to as technology independent. So as long as you know your Boolean algebra, you'll be able to understand, what is the output of this thing. This is extremely important because we may want to take the same circuit and plug different technology libraries. You have already seen that, right? You'll be doing a lot more of it in every homework. We say, oh, this is the technology library. Tell me what is the area it takes? What is the delay that happens in this given technology? So we can do Boolean optimizations. I mean, you have already seen quite a few of them, right? And Bluespec compiler does many of those things. But what Bluespec compiler does not do is take a gate library and take this Boolean circuit and try to produce an optimized circuit, that you may actually want to produce. For that, we use the Verilog compiler. So the output of Bluespec compiler doesn't look like gates directly. It outputs another language called Verilog, which is commercially a very widely used language for hardware design. And then once the descriptions is given in Verilog, then we feed a gate library to it and see exactly what netlist comes out of it according to some optimization criteria in it. So to understand the Bluespec part of it, there are some concepts which are essential to understand, and this often in the jargon is called static elaboration. So in Bluespec, we may use many ideas which have no direct hardware realization. And all such concepts from Bluespec are actually, Bluespec compiler eliminates them at compile time. It will do something to that description so that all these fancy features of Bluespec disappear in the intermediate forms. In particular, all data structures are converted into bit vectors. In other words, the output circuit only knows about bits and nothing else. Right? So this will be true all the way through. Loops are unfolded. So you may write loops in your program, but they will all be unfolded. They'll become acyclic graphs, once we have done the unfolding of it. Any function we write, and you have already written the half adder, full adder, use the full adder to build the ripple carry adder, right? All these things will be eliminated. Functions, we keep substituting them until we get down to the basic gates, from it. So functions are inline. And ultimately, what remains out of all this is an acyclic graph of gates. Now, it's possible for you to write a Bluespec program whereby erroneously you write something which is cyclic. So, for example, I can say x equals and of, y and x. You're trying to define x in terms of x. That's clearly a cycle. You're taking the output of AND gate and putting it right back in. So fortunately for you, well, first part is not fortunate. All such circuits are illegal. Fortunately for you, Bluespec compiler will always detect cycles. And if it says there is a cycle in your program. So it's a very powerful thing, that if you made a mistake, you created a cycle inadvertently, it will be caught at compile time. All right, so with this background, let's, instead of sticking to 2-bit ripple carry adder, let's write a 32-bit ripple carry adder. And I could have used a text editor and duplicated the code, 32 times, what I showed you on the previous slide. And it's tedious, because you'll have to rename things and, you'll have to use 1, 2, 3, because it's not all the same index all the time. As a modern computer science person, you say, why can't I write a loop? Indeed, you can write a loop, right? So you can write this adder, 32-bit adder, in terms of a loop. So here it has 3 inputs, x and y, and carry in, which is 1 bit. And these inputs are 32 bits wide. So the output of my 32-bit adder is going to be 33 bits. Good. I define initial sum bits because I'm going to produce the sum bits out of it and carry bits, and remember the carry bits have to be defined for every stage, but the carry bit from stage I is connected to the carry input to the I plus first stage. And this is what this program represents. So it's telling you the initial value of some bits are 0, carry bits are all 0. I'm emphasizing it again by saying C0 equals C0 in case you have given me, some input carry in bit into the circuit. And now what you see here is a very ordinary loop, which if you're not familiar with this syntax, loop has several parts in it, right? So there is a loop variable. What is the loop variable here? A loop is incrementing some variable here all the time, which is I, right? And what is the second thing there? I less than 32. Is saying, please do this loop until, as long as I is less than 32. And what is the last thing telling us? That after every iteration you increase the value of I by 1. So you always have this, whenever you have a loop, you have some initial value, you have a loop variable, you have a predicate or end condition and the incrementing value, incrementing expression, and after that you have a loop body inside it, which looks like this in this case. Now let's see if this loop body makes sense. So what did I do here? In the ith iteration of the loop, that's how you have to think. Now we're talking of generally the ith iteration of the loop. I'm going to call the full adder. And in full adder, I'm going to apply to the xi input and the yi input. And what is the carry in this case? Ci, and it's producing, which way does it go? Right. And it's producing a carry for the next stage. Carry Ci plus 1. C of the Ci plus 1. Does this make sense to you? Full adder had 3 inputs, an X input, a Y input, and a carry in, and it produces a sum bit and a carry bit. And this carry bit will be used in the next stage, and that's what this recurrence relation is about here. Yes?
If you're doing each full adder one by one, don't you only keep track of one carry bit?
Say that again?
Why do you have 33 bits for the carry? Don't you only have to keep track of one carry bit at every step?
You do. I mean, it's easier to write it like this. I could have, you're right, I could have written C and just pass C on thing and then return C from the loop, which is the last value of C. Yes, it could have been written in that form. But here, the point is that you need all these different C's, right? So we are going to, I've just represented it like that. Very good. And then we are saying that Ci plus 1 equals Cs of 1. Cs has 2 bits in it, remember? Whenever you do full adder, it produces a sum bit and a carry bit. Okay, so the 0th bit in it is the sum bit, which will go in the ith. Si is, CS0, and the CS1 bit is the carry bit for the next stage, which I have put into the carry bit. When I say put, really, I'm just renaming wires. The output of this full adder was called CS, right? And CS0 bit I'm taking from it, and I'm calling it the ith bit of the sum. It's simply a naming thing that is going on. Whenever you see equal sign, there is no computation. It's simply a question of renaming wires over here for the next iteration. And then in the end you return C32, which is the last carry bit that came out of this, as well as all the sum bits. And sum bits, as you may recall, is 32 bits wide here. Does this loop make some sense to you? Right? I mean, if you're familiar with loops in any programming language, more or less this should make sense. Now, what we want to discuss is what kind of gates are generated. In what sense this is a description of a circuit. You all understand the computational meaning. In fact, that's the easy part for you as a computer scientist. What you have to learn in this class is what gates are being generated when I write a loop in this manner. And that's the interesting part here. We unfold the loop, right? Only meaning of a loop in this language is anytime you see a loop, it's going to be unfolded at compile time. Which means if you did not know the value of, that it was 32 long, you won't be able to unfold it. So you have to specify the value, which we wrote down. We say this loop executes 32 times. So this is the unfolding of this loop looks like this. This is the first iteration of the loop. Everybody agrees with this, right? And now I'm going to substitute, instead of 0, I'm going to substitute 1 everywhere. And notice it's automatically connected because C1 that is being used here was defined in the previous thing I wrote, where I said C1 equals CS of 1. So you can keep doing this, right? You can do it 32 times, and if you keep doing it, ultimately you will get this unfolded circuit. So please remember, we write loops, but compiler is always going to unfold them. All right? Always going to unfold them. Now, some subtle language issue here. So this CS is occurring over and over again. But CS is a local variable, so this is the same issue that would have arisen if I had used C everywhere, instead of declaring C as a vector in this. So CS is being reused over and over again. But conceptually, you have a full adder, its output is being called CS. You have another full adder, its output is also being called CS. These things actually all will be renamed. We could have written CS0, CS1, CS2, and Bluespec has its own way of renaming things. You never have to deal with those names, but I'm interested in conceptual clarity of it. So we don't think of that same CS as being used. Every iteration is generating a new CS, so some naming convention you can adopt, and I could have written it like this. That CS0 is this, and CS1 is this, and so on. No change in the program, it's still the same. Does everybody understand that CS was a local variable in the loop body, and when I start copying it, every time essentially I'm getting a new copy of CS. So CS0, CS1, CS2, CS3. Now, such a picture is guaranteed to define an acyclic graph for you. How do you know that? I mean, I can just give you a pictorial representation of this. So you had a full adder, right? That's what you generated in the first cycle. And then you have the next full adder, and they're all being connected to each other. So assuming that full adder had no cycles in it, what we have generated here is also an acyclic interconnection of gates. And once we have done this, we can go and substitute whatever full adder looked like. So first I unfolded the loop, and after that I say all functions are inlined, or they are substituted. And once you do that repeatedly, you will end up with a circuit which, in terms of primitive gates, ands and ors and nots and so on. Okay, and that will be an acyclic graph. So please don't get confused that we have loops here, but in execution there are no loops. The circuits that are being generated are absolutely acyclic, and you will just be unrolling this graph. Okay, let's do one more example, which is multiplication by repeated addition. All right, so you have, 1101 is being multiplied by 1 0 1 1. So you all know the algorithm for multiplication. You just, if it's 1, then you have to, the thing you have to add is, so depending upon the bit in the multiplier, you are either going to add 0 to it, or you're going to add the number that is over there. So if you look at it like this, then since this bit is 1, I have added 1101. So in the next iteration, what do I have to add? The bit is 1 again, so I'll be adding 1101 again. And the next time, bit is 0, so I will be adding 0 to it. And the last time, again, it's 1101 that is being added to it. So essentially, MI is telling you whether you add 0 or you add the multiplicand in it. All right, and we start out with, let's assume the temporary product value is 0, and every time we add something to it. We also shift the result by 1 position on every step. This you must remember from your elementary, whenever you learned your multiplication, right? You keep moving it 1 to the right, because in the first iteration itself, I have already got the first bit of my result. In the second iteration, I get the second bit. All the computation keeps shifting, and after the nth step, I get suddenly 32 bits out of it, and all the bits that are there. Notice the first addition is unnecessary because the value is 0. You may want to express it in your own terms. I won't worry too much about it because the Bluespec compiler is sophisticated enough. When it will see all zeros, it will automatically turn the first level of circuit to nothing but wires, because there is nothing to be added over there. Okay, so now let's see how the circuit realization will look like. For this, so we have already discussed that we have to define an MI for each level, so if in this example there are 4 levels, so for each level I have to define, M0 and then M1, M2, M3, M4, which is telling me what am I adding to it, right? Whether I'm adding a 0 or something else. I already gave you the program for this by saying MI equals, if the ith bit is 0 in the multiplier, then it's 0, otherwise it's the multiplicand. Okay, the question is, how do I connect it? So I'm going to use 4 adders for this. So far so good. In the first adder, what is the other operand? 0, very good. Right, so I put zeros there. And what is the second operand for the second add 4 for that adder?
The output from the previous adder.
The output of the
Adder.
Right, directly, or some shifting has to go on? We can't use bit I don't know which way it looks. The rightmost bit for it. So that one goes out straight. Does this picture make sense? Right? Because we have already computed the first bit, that is the result. And the other bits come here, including the carry. That was the whole point, right? Carry is generated, which I carry forward, right? I keep connecting it to the next stage and the next stage. And I do it again, and I do it again. And finally, I have the result. So one thing to notice right away is when you start out with 4-bit numbers, you get 8 bits, you get much more than 4 bits in this case. And typically you will ignore the larger bits in this. You will only look at the lowest order 4 bits in this. Can you write a loop program to express this idea? So when we wrote our ripple carry adder, what was the main building block inside it? A full adder, right, which I used 32 times. So now when I build a multiplier, what is going to be my building block? Add 32 in it. Indeed, the program looks very, very similar, right? So here is my multiplier description. You know, I'm giving you two numbers, A and B, over there, which are 32 bits. Temporary product is 0, it is 32 bits. And the final product is going to be 32 bits. You know, I'm initializing it to 0. And my loop, again, I want to do it 32 times. And now look at it. What is the very first thing I do? I'm computing whether m is going to be 0 or the multiplier, right? So I'm computing the mth bit. So if AI is 0, then it's 0, otherwise it's the B input to this. Okay, and then I can take this m and I'm adding it to something. I'm adding it to the temporary product, and the input was 0. The carry in for this adder was 0 in this case. Does the next slide make sense? Prod I equals sum 0. Remember, whenever we have an adder, the lowest bit is going right out as the answer. So if you're doing the ith iteration, you're defining the ith bit of the result, right? So that's what is written here, that the ith value of the product is going to be the sum 0 bit, and temporary product is simply the rest of it, you know, 1 to bits 32 that came out, including the carry bit. And then I'm returning here the temporary product as well as the product. So you can see in product, what have I done? And each iteration I have defined a bit of the product, right? So you're finally getting all 32 bits of the product, and whatever extra stuff we have, we are returning that too, just in case. This is a very, very standard way of describing large combinational circuits. And some of the large combinational circuits arise in arithmetic, right? And you have to agree that this is much more pleasing, I mean, to write a loop there as opposed to just duplicating the code over and over again. You're likely to make many more mistakes if you don't use a loop and you try to duplicate the code 32 times, or if I gave you a 64-bit adder 64 times, or 64-bit multiplier 64 times, you're doing it. Good, so let's assume you can write this. Of course, this is going to need some practice for you. Let's think about this a little bit. Okay, this circuit uses 32, add 32 circuits. Pretty soon we are beginning to design big circuits here, right? I mean, do you agree that this is lots of gates, right? I mean, adder had so many gates, and now we are freely using them, and you'll love the power of parametrizations. You say, ah man, I could have designed a 64-bit one also. No extra time, no extra charge for you. But what you cannot forget is if you designed a 64-bit adder or a 64-bit multiplier, that circuit is dramatically larger than 32-bit circuit. Okay, we always have to be thinking in terms of what is being generated, what kind of circuit is being generated. Yes?
Could you explain the return line?
Sorry, say that again?
Could you explain why in the return line there's TB and product? Shouldn't product be full at the end?
Why am I returning TB? I don't have to. I mean, you know, it's generally when we think of product, I mean, when we think of a multiplier, we return the full answer, but in your language what you see, in your assembly language what you will see, depending on how you're going to use it. All these bits are meaningful, right? But if you restrict yourself that I only deal with 32-bit quantities, then there will be restrictions on multipliers so that, you know, the other bits, you don't get there, you know, it shouldn't populate. The answer must be less than 32 bits or expressible using 32 bits. But mathematically there is no problem, and therefore I just returned it over there. So let's analyze this code that I have just shown you. Okay, long chain of gates. What do I mean by this? 32-bit multiply has 32 ripple carry adders in sequence. Why do I claim they're in sequence? Is there a data dependency in how these adders are connected to each other? Right? You're getting some output from the previous adder, a lot of output from the previous adder, which is all being fed into the next adder. So, to the first approximation, long sequences, right? Your signals are going through 32 levels of adder circuitry. Okay, so let's go and analyze the adder circuit. Right? Ripple carry adder has 32 long chain of gates, right? Because it had full adders connected sequentially. So not only is this circuit large, you shouldn't be shocked if its propagation delay is very long, right? Because we have to go through all these full adders and then all these full adders and all these full adders. And actually, this is an interesting question to I wanted to come to the take-home problem first. I want you to think about how much is the delay in this circuit. And if you're sloppy, you're going to give me the answer is 32 full adder square. Right? Whoops. Went here, you have 32 of them. It can be worse than that. The question is it really that much? Or the worst case delay is much better than that? So think about it, right? So this is the problem I want you to think about. Whenever we say take home problem, these are all thought problems, right? You just have to think about them. Because if you understand it, that means you're following the material, and that means you will also do very well on the quiz, right, for these things. Okay, now let me go back to the other two questions. Can we design a faster adder? And the answer to that question is emphatically yes. And I'll devote the whole next lecture talking about faster adders, what tricks we can play so that the propagation delay of adder is less. And as is often the case, you will find there's a trade-off. If I'm willing to introduce more gates, if I give it more gates, then I can bring down the delay of the circuit. Very interesting topic. All right. The other question is even more intriguing. Instead of using 32 add circuits, could have I used just one add circuit, right? Produce the answer from this, store it somewhere, next time use it again, next time use it again. In other words, reuse the circuit over and over again. Only way you can do that is if you have a storage element. We don't have any storage elements yet. So you have to wait for that answer a few more weeks, or at least a week more, 2 weeks, something like that. Okay? It's coming. So yes, answer to both questions is yes, we can design much better multiplier. We can design much better adder. The answer to the adder question you're going to get next time. Answer to the multiplier a little later, probably in some lab. All right. Now let me ask a natural question. Could have I written an n-bit adder? Such things are referred to as parametrized circuits. This looks very simple, right? I mean, all I did was took the same thing and I just, replaced 32 with n's everywhere. You should be able to understand this code, right? I mean, this is almost the same code as what I wrote down for 32-bit adder. Wouldn't it be wonderful if you could write, and if we could do that, then we'll write it once and we'll instantiate it as many times as we want. We'll say, make me a 4-bit adder, make me a 16-bit adder, make me a 64-bit adder, as opposed to taking your code and changing bits in it, right? This is much more satisfactory if we could do this. And this code is almost there. Unfortunately, there are way too many type errors in this code. And for you to understand what these type errors are, I have to first tell you a little bit more about types. Okay, so next few slides are about introduction to types. First thing is Bluespec expression in Bluespec program always has a type. So this is a property of all strongly typed languages. So if you program in Java, there are many languages out there which are strongly typed. Unfortunately, the language most of you know is Python. It's not strongly typed. So there everything doesn't, I mean it has types too in Python, but it's only known at runtime. In Bluespec programs, in Java programs, you have to tell me the type up front. You know, what is the type of something? Okay, so every expression has a type. What is a type? In the simplest understanding of types, type is nothing but a grouping of values. You all understand that. You know, if I say even numbers, right? Say, oh, you mean 2, 4, 6, 8. You think of a set, right? I'm giving you a property, you know, which defines the whole set. Integers, you know, everything. So we can talk of bits. So there are all kinds of types we can, groups of values that we can talk about. So when I write bit 16, it means any value that is being represented as 16 bits, we'll give it the type bit 16. All right, so this is a 16-bit wide bit vector. Bool. When something has a type bool, that means, you know, it's either going to be true or false, and it gets a little confusing because we almost always represent 2 as 1 and false as 0. So, you know, you can think of it in terms of bits also, but bool type is different from bit type. Okay, these are different things. The next one is slightly more interesting. We can have a vector. So once you have defined a type, you can use it to define more complex types. So a vector has a size. In this case, it's 16. And how big is each element of this vector? 8 bits, right? So these are just some sample types. You can have all kinds of all kinds of groupings. Here is a type declaration can be parameterized by other types using the syntax of ampersand, you know, or the number sign. Okay, so bit n represents n bits. So it could be bit 8 or bit 32 or whatever. So here is another one. You have bit tuple 2, whose first component is bit 8 and the next component is integer. In this represents a pair of 8-bit vector and an integer. Even functions have a type. So if I give a function to you and I say, you know, it has 8-bit arguments and it returns an 8-bit result, so essentially its type is all those functions which, given an 8-bit input value, produce a 8-bit output value. Who's going to tell me what is the type of an half adder? What is the type of an half adder? What are the arguments it had? Yep. You have to regard separate arguments as separate ones.
Oh, no,
2 1-bit numbers, right? And it produces 2 bits. So that is a signature. I may often use the word signature. What is the signature of a function? All these ideas are very useful because we will use this information, and if signatures don't match, you know, system will complain. No. You know, you're trying to confuse me. You know, these things you're trying to connect to each other, they don't make sense anymore. This is a Bluespec thingy, right? That a type name always begins with a capital letter. Whenever I say the word always, there's always an exception. And the exception turns out to be bit. Bit can be written with a small b. Forget about exceptions. Type names are always written with a capital. They always begin with a capital letter. And all other variable names are written with small letters, including type variable names. Right? So you can have. The other concept about types, which you will love as you go ahead with this, is the notion of synonyms. So instead of writing bit 8 all the time, I may want to say, oh, this is a function that works on bytes. Okay, so I declare type def. What is a byte? It's 8 bits. So from now on you can use byte wherever you wanted to use bit 8. It has become a type. It's a type def for byte. Type def for a word is 32 bits. And the moment we do that, now I don't have to keep writing bit 8 or bit 32. I can start using, oh, this is a function on bytes, this is a function on bytes and words, etc. So it's very syntactically very pleasing. It's more intuitively obvious what's going on in this case. So here is a tuple, and here I'm introducing a type variable. So I'm saying a tuple of two values, two things, both of type A. Right? I haven't told you what type A is, so I could have called it a pair A, and here notice a variable. So the beauty of this is any time I use a variable, that means you can write any other type expression in it. It'll work. So you can define a pair of any things you want. You can define a pair of pairs, or you can define a pair of integers, or a pair of 8-bit numbers, etc., etc. A pair of functions you can define. Anything is possible. This is a very interesting type. It's a numeric type. I'm saying I want to call, data size 32. Instead of, just writing 32 every time, I'll say data size, and I mean 32. So even though it's a number data size, I'm going to use it as a type. And here I use it. So I'm saying bit data size data. Who can parse this for me? What is this last declaration, type def, saying? You are saying data is bits, right? How many bits? Then we have to go and read data size. Data size is 32 bits. So instead of writing bits 32 data, this is done in 2 levels. Yep.
If you had this in your code, would there be any difference between how you use Word and data?
Say it again?
Would there be any difference between how you use Word and data if you had it set up like this?
There'll be, you can use Word here, yes? But here, inside bit, you could have used word size. Yes? Mm-hmm. All right. No, sorry. What am I saying? No. Type of word is something else. What is the type of a word?
It's 32 bits.
It's 32 bits. It's not number 32. Data size is 32.
The line underneath is bit 32.
Which line?
The last line.
Bit data size is also bit 32.
Oh, you're saying could have I written word there? Yes. Sorry, I misunderstood. It's very important to distinguish the numerical 32 versus bit 32, because that's 32 bits. Okay, good. Thank you. This is another one which is very interesting, enumerated types. A very useful concept. In type, suppose we have variable C whose value can be represented in 3 different ways, right? So not in 3 different, you have 3 different colors. So as a programmer you say, oh okay, red will be 0, 0, green will be 1, 0, and whatever, You assign some representation and you can write your program, you're happy, fine, right? A better way is to actually declare a type, and we do this using enums, enumerate. Enum stands for enumerate. And we are saying, there is something called a color, a type called color. And color has to be one of these, right? It has to be either constant, marked red or blue or green. Okay, so why am I doing this? Bluespec compiler will automatically assign a bit representation to this. It can do whatever it wants. It can say, representation of red is 1, 1. You wouldn't know that. Okay? And it can also automatically generate the equality function, because you may want to test if two colors are the same. You could have written such a function yourself, but compiler is just being helpful to you, so that's what deriving stuff is. It's saying, I'm giving a new type to you, compiler, Mr. Compiler, please, give me the bit representation of it and also define the equality type on it. And there are many such functions you can define automatically just by writing derive this for me. If you are not using derive, then you would have to give the representations, etc., which I do not recommend. All right, so why is this better? Anyone? Why is, yes?
It's an abstraction.
It's abstraction, right? It's going to let you avoid certain kinds of errors. So for example, suppose I had something else also. I had sizes, large, medium, small, and I also use bits to represent those sizes, 1, 1, 1, 0. You could inadvertently, if you were expressing everything in bits, you could inadvertently compare the size with the color, which is clearly wrong. I mean, they're wrong types, pardon the pun, right? So by declaring these things as types, things have to be of the same type before they can be compared. You'll be amazed how many silly errors it will avoid. So once you start using enum types, please use them generously, right? And use good names so that it helps everybody reading your code. Okay. So the next important concept here is type deduction. So I keep saying that if you make a mistake, compiler will catch you. So suppose this is the code you had written, and by mistake, instead of writing 2, there you wrote 3. Now compiler actually can deduce that you have made a mistake. Any ideas how compiler will deduce that this is a mistake? Compiler knows, if you see it, what is being returned. If you look at the expression inside, you are returning C out and ABC 0. How big is C out? 1 bit. How big is ABC? 2 bits. How big is ABC 0? So you're returning 2 bits, but your definition claims you're returning 3 bits. Compiler doesn't know who made the mistake in this. All it knows is inconsistency, right? So anytime it detects an inconsistency, it tries to point out. Not it tries, it will always catch it. It may not be able to pinpoint exactly where the inconsistency came from, but it gives pretty decent messages, right? So you'll say, sorry, this code is not right. You have to first fix the types. So when you're not used to types, in the beginning there is some frustration. You say, this seems reasonable to me, and the compiler keeps complaining, sorry, type error, type error, type error. So you go through this hate period in the beginning, and then the love affair will begin, right? Because just types, when they work, they save you so much hassle that all such complaints will disappear after 2 weeks. Okay? In fact, compiler can reduce the programmer's burden. Actually, compiler can we provide extra syntax to reduce your burden of types. And this syntax is known as the let syntax. So let me just show you what that will do. So let syntax is that you have f of a, b, and c. This is the same code that I have shown you. But look, compiler, actually you can write just lets here instead of writing bit 2, bit 2, bit 1. Compiler, if you just write let's there, you're asking the compiler, please deduce it for me, right? Fill in the right number. How does the compiler know what is the size of HA? How does it know that AB should be 2 bits? Because somewhere else you have declared HA. So because it knows HA is 2, then this must be 2, right? So this is the role of lets. It just, it's a convenience. It's a convenience. If you don't like them, just keep writing all the type definitions. But I will be using it quite heavily in the lectures. So the last problem, which I won't be able to finish, but at least let me point out the problem. So I wrote you this code which seemed very reasonable, and it has all kinds of types error in it. So all the places I have marked are type errors. System doesn't like the fact that I used n plus 1 there. Why? Because n in this case is clearly a type thing. I'm saying this quantity is, the type of this is n bits wide. N is a type thing, numeric type. We don't know how to do arithmetic on type thingies. So when you say n plus 1, compiler says, what? I don't know about that, right? Same thing is true when you compare I to n. N is a type thing, right? And the subtle aspect of this is every expression in Bluespec has a type, and many expressions in Bluespec have a value. And values and types live in disjoint universes. They never mix, right? So if you want to pull one, if you want to ever pull something from the types world into the value world, you will have to say so explicitly. And if we do all those things, we can fix it, and then I won't show you all the fixes, I'll just give you the fix code. So you write type add over there, and instead of writing just n, you say value of n, and if you do it like that, then this code becomes type correct at that point. Takeaway, once defined, you have defined a combinational circuit, we can use it repeatedly to build larger circuits. Bluespec compiler, because of the type signatures of functions, prevents us from connecting things in a silly way. We can use loop constructs and functions, and they're all unfolded. And finally, advanced concept is this parametrized types, which we'll follow up in the recitations. Okay. Thank you.